Last lecture, we discussed the oxidation and rearrangement reactions of glycols. With this, we conclude the alcohol portion of this chapter, and today we are going to continue with another topic from this module, that is phenols. Okay, so our today's topic for discussion is phenols, and the general structure, the chemical structure which represents phenols is given like this. Phenols are essentially a hydroxylated benzene. Okay, so it is a hydroxy benzene. It is also known as carbolic acid. Phenols are also known as carbolic acids. If you look at this structure of phenol, the hydroxy is attached directly to this sp2 carbon, which is a part of the benzene ring. If I rewrite this structure in another manner, for the same phenol, this is the structure of cyclohexa 2,4-diene 1-one. So, this essentially represents the keto form of the phenol. So, this can change to the enolic form, which is actually the phenolic form in this case. So, this is the keto form and this is the enol form of this molecule, and this is what we call as the Keto-Enol Tautomerism. So, the Keto-Enol Tautomerism exists in case of phenols, and the enolic form, that is the phenol in this case, is the major contributor, and the keto form contributes in a minor way. That is why if you look at this equilibrium, it is more towards the enolic form and less towards the keto form. The stability of the enolic form can be understood in terms of the aromaticity acquired as a result of enolization. So, this aromatic ring is what is the driving force for the enolic form to predominate. Okay. So, this is the thing which exists, because in this case there is only the carbonyl, one carbonyl, which is giving you more stability over a carbon-carbon double bond, right. But in the case of a phenol, it is the aromatization which is a driving force. Okay, let us look at some of these examples of phenolic compounds. If you have a simple phenol substituted with a methyl group at the ortho, meta or para position, which I can represent like this, it becomes a orthomethyl, a metamethyl or a paramethyl phenol, and these methylated phenols are called cresols. So, the methyl substituted phenol is called cresol, and if you see, this is isomeric with this molecule, which is nothing but your benzyl alcohol. So, cresols are isomeric with benzyl alcohol, but this is not a phenol. A benzyl alcohol is an aromatic alcohol, right. This is an alcohol, this is not a phenol, it is an aromatic, aryl ring containing alcohol, but a phenol is OH is directly connected to the benzene ring. So, the two have significantly different properties. Okay. Likewise, there can be other aromatic alcohols, and if you have to name these aromatic alcohols, so you would take this as the preference 1, 2, 3. So, you say that this is a 3-phenyl propanol, but these are aromatic alcohols, they are different from phenols. The most important application of phenols is found in the phenol formaldehyde resins. Okay. The phenols are important precursors to these polymers, and there is where it finds its principal use. Let us see some of the methods of preparation of these molecules. So, the preparation of phenols can be carried out on an industrial scale and at lab scale. Let us see some of the methods for the industrial preparation of phenols. So, to get the bulk amount of phenol on the industrial level, one of the methods which is used is from the coal tar distillation. So, it is a natural source, the coal tar, and when we carry out the distillation of the coal tar, we get different fractions from the fractional distillation. We get the light oil, the middle oil and the heavy oil fractions from the coal tar distillation, and it is the middle oil fraction which comprises of mixture of phenols and naphthalene. Okay. So, it is this middle oil which is then subjected, middle oil fraction is subjected to subsequent treatment from which pure phenol can be isolated. So, this is on the industrial scale for isolation of phenol, and the boiling point of pure phenol lies in the range 180 to 182 degrees Celsius. Another method on an industrial level for the preparation of phenols is from chlorobenzene. Starting from chlorobenzene, phenol is prepared by a process which is known as Dow's process. Okay. It is popularly called the Dow's process, and in this what is done is that chlorobenzene is treated with aqueous solution of sodium hydroxide at a high temperature and under pressure. Okay, so, it is treated at a high temperature and pressure, and under these conditions it results into formation of sodium phenoxide, which on acidic workup gives us the corresponding phenol. So, this is called the Dow's process, and in this the formation of the phenol is believed to occur via a benzyne mechanism. So, I am sure you must have studied the benzyne mechanism, the elimination addition pathway. So, that is the intermediate involved in the substitution of the chloro group by the hydroxy group, because it is kind of a nucleophilic substitution reaction, and we know that aryl chlorides or aryl halides for that matter are not very easily susceptible to substitution nucleophilic. Therefore, since we find this to happen, the mechanism has been proposed to go via a benzyne intermediate. Another method for the industrial preparation of phenol is starting from cumin. Cumin is also known as isopropyl benzene. So, we start from isopropyl benzene or cumin and treat it with air. So, under oxidative conditions it yields an intermediate which is a cumin hydroperoxide. So, you get this as the intermediate, which is cumin hydroperoxide. This is your starting cumin, you subject it to aerial oxidation, you get this intermediate, and this on treatment with acid results in the formation of phenol along with generation of a ketone, which is nothing else but acetone. So, you get the phenol and you get acetone as the byproduct from the cumin oxidation. So, in going from the hydroperoxide to phenol, we believe what is happening is that there is a migration of this phenyl group. So, this reaction it involves the migration of this phenyl group to give you this intermediate. So, you get this intermediate, the phenyl group migrates towards the oxygen, you get this intermediate with this carbon bearing a positive charge, and then you get this intermediate in which you have two leaving groups on an sp3 carbon. So, this leaves, okay, and from here this is what you get, the phenol and formation of acetone. So, this reaction is a commercially successful process of making phenols. Okay. So, this is a commercially most successful method of making phenols, starting from cumene, and cumene can be easily prepared from benzene treatment with propene. So, you can easily get cumene. So, this is an acid catalyzed reaction. Okay. You get the cumene, and cumene on aerial oxidation gives us the phenol and acetone. Okay. These are some of the industrial methods for the synthesis of phenols. Let us see what are the lab scale preparations. The lab scale preparation of phenols. So, in this there are again several methods. The first one I am going to discuss is starting from sulfonic acid. From sulfonic acid as the precursor, this is actually called the alkali fusion of sulfonates. So, you have alkali fusion of sulfonates. So, in the presence of the alkali, what happens, that you have your sulfonic acid. In the presence of alkali, you get the sodium salt of sulfonate. Okay, so, this is your starting precursor, your sodium aryl sulfonate, and this is subjected to fusion with the alkali. Okay, so, you treat it with NaOH, aqueous conditions at 300 degrees centigrade. So, this is the fusion step where you get sodium phenoxide along with formation of Na2SO3, and this then upon acidic workup gives us the phenol. Okay. So, in this case you get the phenol, and your aryl can be anything. You could have a phenyl, you could have a substituted phenyl, okay, a toluene, any of these groups. So, this is a method, a lab scale method for preparation of phenol starting from sulfonic acids as the substrate. The next method is by hydrolysis of disonium salts. So, it is starting from disonium salts and carrying out its hydrolysis in aqueous acidic solution. So, you have a disonium salt, you subject it to acidic hydrolysis at a certain temperature. So, the reaction involves heating, and you get the phenol along with the liberation of N2 and HX. And the disoniums we know are easy to obtain starting from the aryl amines, and the aryl amines again you have studied that you can always prepare starting from benzene, subjecting it to electrophilic substitution, nitration in this case. You get the nitro substituted benzene, reduce it with tin HCl, you get the arylamine, and the arylamine can be subjected to diazotization with NaNO2 HCl at low temperature, when you get the diazo compound, which can then be subjected to this hydrolysis, acidic hydrolysis under heat, and you get the phenol and nitrogen in HCl. So, this is essentially a very straightforward method starting from the disonium salt hydrolysis. Another method is from Grignard's reagent. you take the Grignard's reagent, in the presence of air treat them with oxygen, and this is followed by again a dilute acid hydrolysis. So, what happens overall? You start with the aryl Grignard's reagent, phenyl magnesium halide. In the presence of oxygen, it forms this OMgX, which upon acidic hydrolysis, acidic workup, gives you the phenol and this magnesium salt. So, these are some of the methods for the lab scale preparation of phenols. Let us now look at some of the physical properties of phenols. So, when you see a phenol, there is a hydroxyl which is attached to this carbon, which is sp2 hybridized and part of the aromatic ring. If you look at the physical state, these are usually colorless liquids or they are low melting solids. So, if you look at a phenol for that matter, simple phenol unsubstituted, it is a solid with a melting point 43 degrees centigrade. It is a low melting solid, but it has a high boiling point of 182 degrees centigrade, and the high boiling point you can imagine can be attributed to the hydrogen bonding property of this molecule which we discussed earlier. The other thing they possess is a typical carbolic odor. Because of this hydrogen bonding ability of the phenols, it is also possible to solubilize them in water. So, they are moderately soluble in water, because you have two parts, you have the hydroxyl which is solubilizing it, but you also have this bulky aryl group which is hydrophobic, and that is why they are moderately soluble in water, and therefore, they are also soluble in organic solvents. Just the way the amines are highly susceptible to oxidation, the lone pair of electrons on oxygen, it also makes them a good candidate to get oxidized. So, the phenols get oxidized easily, and if you keep them over a period of time, some color develops in these phenols. Okay. So, these are prone to oxidation just like amines. So, these are some of the typical physical properties of phenols. Let us now look into some of the reactions which they undergo, and at the same time let us compare them with what we have learned earlier with respect to the alcohol. So, I am going to divide the reactions into two categories. One, as we did for the alcohols earlier, one is due to the OH group, and the other now in this case is going to be due to the aryl nucleus. So, unlike the alkyl part here, you are dealing with the aryl. So, what are the reactions typical of the aryl nucleus and due to OH group, and because of the hydroxyl again you can have two types: A, those reactions which resemble alcohols. So, you know that this was happening with alcohols also, and B, those which do not resemble alcohols. Okay. So, let us take each of them one by one. I start with the reactions due to OH group, and in here I take those in which the phenols have a resemblance to alcohols. Let us look some of those reactions in which first a hydrogen is replaced. When a hydrogen is replaced in an alcohol, the first thing, if you remember, we saw was the reaction with a sodium metal. So, the way alcohols were reacting with sodium metal, phenols are also capable of reacting with the sodium metal. It is because of the acidity of this phenolic OH, and it gives you the sodium phenoxide along with the elimination of the hydrogen gas. So, the reaction is similar to what was seen for alcohols. Okay. The other reaction which is similar to alcohols is the acylation reaction. So, you treat the alcohols with acid chloride, acetic anhydride, and you get the corresponding esters, right. So, you take acetyl chloride, treat it with phenol, okay, and what you get is this ester which is phenyl acetate. We will discuss later that this phenyl acetate is susceptible to a rearrangement reaction, okay, which is called a Fry's rearrangement, where this acyl group is going to get lost from this position and going to be a part of the aryl ring. Okay. So, this ester, right, in the presence, if this reaction is carried out further in the presence of any Lewis acid, this is going to migrate to an ortho or a para position in the benzene ring. Okay. So, that happens under the influence of a Lewis acid, but otherwise if you carry out the pyridine assisted acylation of the phenol, you end up with a phenyl ester. Okay. So, in this case all your esters will be phenyl esters. Okay. Another reaction is benzoylation, similar to alcohols. In this you treat it with benzoyl chloride in aqueous NaOH, okay, and this reaction is popularly known as Shorten Bowman reaction. So, you start with your benzoyl chloride, treat the phenol in the presence of aqueous sodium hydroxide. You just shake these and you immediately see the formation of this ester, which is phenyl benzoate along with NaCl water, and this is called the Shorten Bowman reaction. Okay. Phenols can also be treated with benzene sulfonyl chloride, and in this case we get what we call as the tosylates. And tosyl group is a very good leaving group, as you might have come across in the nucleophilic substitution reactions. So, to prepare these tosylates, this is what you do. You start with benzene sulfonyl chloride and you treat this with phenol. It gives you the sulfonyl ester. So, you get C6H5 SO2 O C6H5, and these compounds are called tosylates. It is a phenyl benzene sulfonate. Okay. The same thing which was happening with alcohols, it can happen with phenols also. When you treat them with alkyl halides in alkaline conditions, and this reaction is what is popularly known as the Williamson's synthesis. Okay, so the reaction involves the formation of alkyl aryl ethers. So, it is a very popular reaction for making alkyl aryl ethers. You start with the phenol, which under alkaline condition exists in the form of sodium phenoxide, and you treat this with an alkyl halide. Okay. If you treat it with methyl chloride in aqueous NaOH, it undergoes the nucleophilic substitution reaction to give you the alkyl aryl ether, which this one is called anisole. So, this is essentially a nucleophilic substitution reaction for the preparation of the alkyl aryl ethers. The interesting thing in this reaction is that when you have to prepare the alkyl aryl ether, so there can be two combinations for preparing the same alkyl aryl ether. The question is, what do we do? Which alkyl halide do we start with and which phenoxide should we start with? For example, okay, I will take one example for this. Suppose we have to make this molecule, which is phenyl N propyl ether. There can be two routes or two combination of reagents which can be used to arrive at this molecule. In one case, you can start with this alkyl halide and the sodium phenoxide. The other could be that you start with this sodium alkoxide and treat it with, you treat this with the aryl halide. So, two routes are possible to arrive at this product. So, the question is, which is the combination of substrates that one will choose over the other. So, I put a tick here that this reaction is feasible, but this reaction is not feasible. Now, you think why? Because it involves a nucleophilic substitution. So, when we have to carry out a nucleophilic substitution on an aryl halide, it is not very easy. Okay. So, the aryl halides have a low reactivity towards a nucleophilic substitution reaction. Therefore, we will not choose a aryl halide as one of the reacting species. Instead, we will choose the corresponding phenoxide and take the alkyl bromide to form this alkyl aryl ether. Okay. Let us look at now few of those reactions resembling alcohols in which the hydroxyl group is replaced. So far we were talking about cases in which the hydrogen of the phenol was replaced. When the hydroxyl is replaced, there is one example, the reaction with PCl5. Okay. So, in this case you take the phenol, you treat it with PCl5. When we were taking the alcohol, we were getting the corresponding alkyl halide. In this case, however, the reactivity of a phenol OH to get replaced by the chlorine is not so facile. Okay. Why? Because we know that a nucleophilic substitution on the aryl ring is very slow. Okay. So, this will not work so easily. However, if we make this substituted with electron withdrawing groups, okay, like a 2,4-dinitro phenol, and then we carry out the reaction with PCl5, then in this case we can get the corresponding chloro derivative along with the formation of these molecules. So, for this we have to have a electron withdrawing substituents which activate this carbon and make it more susceptible towards the nucleophile substitution reaction. Okay. So, this is the similarity and the difference with respect to alcohols with which it will happen very fast. Likewise, reaction with ammonia. So, in this you take the alcohol, the phenol, and you heat it at about 250 degrees centigrade in the presence of anhydrous zinc chloride. So, this is the reaction with another nucleophile, that is the ammonia, and you take the phenol, you have to react this with ammonia. This is done at about 250 degrees centigrade in the presence of anhydrous zinc chloride to give you these aryl amines as the product. So, however, the OH substitution is more facile in alcohols as compared to that in phenols. Okay, let us look at the other category of reactions in which phenols do not resemble alcohols. Let us see those reactions in which the phenols do not resemble alcohols, and the first in this list is the reaction with ferric chloride solution. So, the action of ferric chloride solution. So, this reaction is actually taken as a test for identification of phenol. So, it is a qualitative color test for identification of phenols. This tells us if the OH group is attached to the aryl core. Okay. So, the reactions in which phenols do not resemble alcohols is by virtue of the fact that OH group is attached to the aryl core, and this is what makes them different from alcohol. So, the action of ferric chloride solution on alcohol on the phenol gives you a violet, green, purple, red color. So, there is an appearance of all these different types of colors depending upon the type of phenol you are using, and this happens due to the formation of ferric complexes of ferric chloride with phenol. So, the ferric chloride solution gives a positive test, or it gives a color change. A ferric chloride solution is orange in color, yellowish orange. So, it will change to all these different colors if it sees any of these enols or phenols, and enols and phenols give a positive ferric chloride test. So, this is what is not given by alcohol. So, you can distinguish that the hydroxyl containing compound is an alcohol or a phenol. Another reaction in which they are different is the reaction with zinc dust. You heat the phenol with zinc dust, okay, you heat it, and what you get is the reduced form of the phenol, you get arenes as the product. Okay. So, the phenols on treatment with zinc dust are reduced to arenes. Okay. Another difference between them is based upon the acidic nature of phenols. Okay. So, the acidic nature of phenols, the acidity of phenols is not the same as that of alcohol. So, if I have to draw a comparison, a carboxylic acid being most acidic and an alcohol being least acidic, in between comes the phenol. Okay. So, the acidity of phenol lies between the carboxylic acid and the alcohol, but a phenol is about 1,000,000 times more acidic than alcohols. Okay. It is 1,000,000 times more acidic than alcohols, but still it is a weak acid. So, because of the acidic nature of phenols, what are the different things it does which are not given by an alcohol? One, it turns a blue litmus red. Okay. Second, it dissolves in alkali. It dissolves in alkali completely because you get the corresponding sodium phenoxide. So, it dissolves in alkali. The other thing is, which is similar to an alcohol but different from a carboxylic acid, is that it does not give no effervescence with sodium bicarbonate solution. Okay, it is not acidic enough to release carbon dioxide on treatment with sodium bicarbonate. So, if we look at the acidity of phenol, in aqueous solution, it is weakly acidic and can give you this phenoxide ion. Okay, so, this is a weak acid and this is a strong base, and this is a very stable base at the same time. So, if you look at the structure of the phenol and the phenoxide ion, so we know that a phenol can exist in all these resonance stabilized structures with the charge accumulating at the ortho and para positions. Okay. And if you look at the phenoxide ion, in this case the charge is in fact much more concentrated, okay, and the phenoxide ion is stabilized again by resonance. So, it is stable because it is stabilized by all these resonating structures. Okay, it is stabilized by resonance, and that is why it has this ability to lose the proton, because the corresponding phenoxide anion which is produced is resonant stabilized. So, the pKa of the phenols in water at 25 degrees centigrade, a simple phenol, it is 9.89. Okay, let us compare some of the pK values of the differently substituted phenols, so as to get an idea of how the acidity varies according to the electronic influence. So, if you have phenol or 2-methoxy or 2-methyl phenol, which we say is a orthocresol, or a 3-methyl phenol or a 4-methyl phenol. So, I am talking about orthocresol, metacresol and paracresol. Okay. If you have a 2-chlorophenol, a 3-chlorophenol, a 4-chlorophenol, a 2-nitrophenol, a 3-nitrophenol, a 4-nitrophenol, or if you have di-substituted, a 2,4-dinitrophenol or a tri-substituted 2,4,6-trinitrophenol, which has the common name picric acid. So, the acidity is comparable to an acid, so it gets the name picric acid, and compare it to cyclohexanol. So, the pK values of these different phenols and cyclohexanol is of the order 9.89. With 2-methyl phenol it increases. Okay. So, a lower pK shows it is more acidic. Here it is increasing because the methyl group, it increases the electron density on the ring, and therefore, the acidity of the OH bond decreases. With a 3-methyl, so when you change the substitution from 2 to 3, so at the meta position it is less influencing, and the pK is therefore little lower than the ortho substituted isomer. So, it is 10.01. With para it is similar to ortho 10.17. With the 2-chlorophenol, now the chloro applying its minus I effect, okay, the inductive effect, the acidity increases and the pKa reduces to 8.1. With 3-chloro the inductive is lower, little less because it is away, and therefore it is, and there is the mesomeric effect, okay, as well, which is operating in case of these chloro, it is 8.80. With 4-chloro, okay, the pKa is further low, it is 9.20. 2-nitrophenol, very strong electron withdrawing, it is the minus M effect which makes it most acidic, more than that of the simple phenol, and the pK becomes 7.17. With 3-nitro the minus M is not operative, it is the minus I, you have 8.28. With the 4-nitro derivative it is similar to the ortho 7.15. With the dinitro substitution it becomes more acidic 3.96, and that is why we saw that in this case the substitution was happening with PCl5. With a 2,4,6 nitro it becomes 0.38, and compare it to a cyclic alcohol, the cyclohexanol, which is 18. So, this is a rough estimate of the pKa values and the effect of different electronic substituents at different positions on the aryl ring of the phenol and the relative influence it has on the acidity behavior of these molecules. Okay. All right. So, this was about the reactions with respect to the hydroxyl group. Now, we move on to the second aspect of the phenol reactions, that is the reactions of the nucleus. What happens from the nucleus perspective? So, in this the first example I am taking is hydrogenation reaction. Hydrogenation is you are reacting the phenol with hydrogen in the presence of a catalyst, a nickel catalyst in this case, and you heat it, right, and you get the reduced product, and the reduction of the aromatic core is what is taking place, and you get cycloalkanols. This is what you get. So, you start with the phenol, treat it with hydrogen, 3 moles of hydrogen will be required for complete reduction of all the 3 bonds of the aromatic ring in the presence of nickel as the catalyst, and you get the reduced product, your cyclohexanol. The more important reactions of the nucleus are the electrophilic substitution reactions. The electrophilic substitution reactions are the reactions in which the electrophile comes and attacks onto the benzene ring or the arene ring, and this you must have studied when you did the aromatic hydrocarbons, the reactions on a benzene ring. Okay. So, the different types of electrophilic substitutions you know are halogenation, nitration, sulphonation, Friedel-Crafts reaction. All these are also possible on a phenol, but they have a different reactivity pattern which follows for the phenols. So, what happens is that your hydroxyl group, it activates the benzene ring, and because it activates the benzene ring, the relative reactivity of the phenolic aryl core towards the electrophilic substitution is much more as compared to the unsubstituted one, which is a simple benzene. So, let us see one by one what happens with the different electrophilic substitution reactions. Halogenation as the first one. So, one thing which we know that because of the hydroxyl group, our ring is activated. Okay. So, the OH is an activating group, and as we just saw, it activates the ortho and para position. So, the ortho and para positions are electron rich right, because of the hydroxyl group activation there is a more charge at the ortho and para position, the negative charge, by virtue of which the electrophile will prefer to attack at these sites. So, in halogenation reaction, you start with a phenol and let us take examples of a bromination reaction. You treat it with bromine. Okay. Now, I will take two conditions. You treat it with bromine water is the one condition. If you do so, you get not a mono substituted or a di substituted, but you get a tri substituted, tri bromo substituted phenol. Okay. You get a tri bromo substituted phenol if you treat it with bromine water. If you treat this with bromine in a non-polar solvent like a CS2 or acetic acid at low temperature at 0 degrees centigrade, you are able to control the reactivity, the electrophilicity of bromine. So, the reactivity of bromine is reduced when we carry this out in a non-polar solvent and at low temperature, and under such conditions we end up with a mixture of mono substituted ortho and para products, with the para bromophenol being the major product. So, this is the major when we carry out the bromination at 0 degree centigrade with carbon disulfide as the solvent. So, as is expected, because the nucleus is highly activated because of the hydroxyl group which has given its electrons at the ortho and para position, the reaction yields a mixture of the ortho and para substituted products, and this bromine reagent what we are using, source of bromine generation, we call this a bromate bromide method. So, your bromine water, okay, what you are using comes from a mixture of, we can use a mixture of potassium bromate plus potassium bromide. So, it is a bromate bromide method. All right. Another example of electrophilic substitution is sulphonation. What is happening in sulphonation reaction? Compare it to the sulphonation of benzene. Okay. Okay. One more thing I would like to point out in bromination is, you just notice that under the conditions of bromination, the Lewis acid has not been used, is not required for bromination. So, you remember that with benzene ring we were making use of Lewis acids to activate the conditions and helps in the generation of the electrophile. Okay. So, it increases the reactivity of the electrophilic substitution, but with phenols this is not required. Okay. Sulphonation, you start with the phenol, you treat it with concentrated H2SO4, the temperature is ranging in the range 15 to 25 degrees centigrade. The product which you get is the ortho sulphonated phenol. Okay. You get the ortho substituted phenol, and if the same reaction with concentrated H2SO4 is carried out at 100 degrees centigrade, we get the product which is a para substituted phenol. So, in this case we get the para isomer, and if you heat the ortho isomer at 100 degrees centigrade, it gets converted to the para isomer. And if you carry out this reaction with concentrated H2SO4 at any temperature in the range 30 to 100 degrees centigrade, you end up with a mixture of ortho and para. So, this three different conditions tell us that what is happening is that when the reaction is carried out at low temperature, we are getting one product, the ortho substituted, which is a kinetic product. So, we are talking about the kinetic versus thermodynamic stability of substitution in this case. When we carry it out at higher temperature, we are getting the more stable, the thermodynamically more stable product. So, we say it is a thermodynamically controlled reaction. So, we get a thermodynamic product, and if we heat it at high temperature, so sulfonic acid is a very bulky group. It is a bulky group and it will not like to stay at the ortho position next to hydroxy, and therefore, it will migrate, it will prefer to stay at the para position at a high temperature, because that is not the most thermodynamically favorable position for the stay of the sulfonic acid. It is a bulky group. So, that is why a para substituted product is thermodynamically favorable and the ortho one forms as a kinetic product at low temperature. Okay, another reaction in this is the nitration reaction. You start with phenol, you treat it with dilute nitric acid, 25% nitric acid, temperature is 25 degrees centigrade. You get orthonitro phenol, okay, and you get paranitrophenol. So, you get a mixture of ortho and para isomers, with the ortho being the major and para being minor. The same thing, if you carry out, instead of dilute nitric acid, you use concentrated nitric acid, you get not a mono substituted, but a trinitro substituted phenol, which is called picric acid. But the thing is, the yield in this case is still not good. So, you saw that the yield here also, the percentage conversion, it is a 30 to 40% yield and a 10% yield. So, yields are poor in case of nitration. Okay. So, nitration results in poor yield of products, and this happens because of oxidation of the starting material as a side reaction. So, the starting phenol gets oxidized, as I told you, it is quite prone to oxidation. So, in the presence of nitric acid, it undergoes oxidation and it gives you more of the oxidative side products and less of the desired nitro derivative. So, a better method to execute this reaction and get the nitro derivative is that you first sulfonate it, you treat it with sulfuric acid, and we just saw that when you do this in any of these temperature ranges, you end up with a mixture of ortho and para sulfonic acid, but the yield in this case is good. Okay, it is not at least getting oxidized, the core is not getting oxidized. So, when you get the mixture of this ortho and para, now you subject it to nitration. Okay. You treat this with concentrated HNO3, and when you subject it to nitration, here you get 2,4,6 trinitrophenol, that is the picric acid. So, here you get this in good yield. So, you first convert it into the sulfonic acid derivative, and the sulfonic acid, it is a good leaving group. Okay. So, it facilitates the reaction. Okay. And the second thing is that because it is present, it deactivates the benzene, prevents it from oxidation. Okay. It deactivates the benzene nucleus and prevents its oxidation, which was happening because of this OH group, right. So, it prevents the oxidation by deactivating the benzene nucleus of the phenol, and then it is easily replaced by NO2. So, this method for making picric acid is better in terms of the yield as compared to a direct nitration. Okay. Another reaction which involves an electrophilic substitution is the Friedel-Crafts reaction. It is a Friedel-Crafts alkylation which I am going to discuss today, which involves the treatment of the phenol with alkyl halide in the presence of a Lewis acid to give alkyl phenols. So, you take the phenol, okay, treat it with alkyl halide in the presence of the Lewis acid, you end up with a mixture of ortho and para alkylated phenols. If you start with the phenol and treat it with a bulky alkyl halide like a tertiary butyl chloride, this is a case which selectively gives only the para substituted product. So, in this case the alkylation happens only at the para position, unlike the other case it is by virtue of this, you say virtue, or it is because of the steric hindrance offered by the tertiary butyl group. Okay. Another reaction I am going to take in this electrophilic substitutions is the nitration reaction. So, in the nitration, what is happening? You replace the H by NO. Okay, so, your electrophile is NO plus, and you know that NO plus is a weak electrophile, yet it undergoes a reaction onto phenol. So, your reaction involves treatment of the phenol with nitrous acid. So, you take the phenol, treat it with nitrous acid at low temperature, and it undergoes a nitration. So, the ortho position is blocked here, it undergoes nitration at the para position, and the nitrous acid can be generated, we know, from the corresponding nitrite salt in the presence of the acid. So, this is how you generate nitrous acid, and this nitrous acid is capable of carrying out the nitration of the phenol, and this is one of the examples where an electrophile like a nitrosyl ion can be added, it can be the phenol can give us the nitrosylated phenols. Okay, so, I stop here with the electrophilic substitution reactions. There are still many more reactions of phenols which we have to discuss, but I will stop here, and next class we will take up another very important reaction of phenols, that is the Reamer-Tiemann reaction. But till then you can just go through all this and revise and gear up for the next class. Thank you.